Well, hello, I'm Marty Pagel, and I would like to present the topic of magnetic resonance imaging. This is part one of a two-part series, and this part will describe how MRI works. I'm a professor in the Department of Cancer Systems Imaging and the Department of Imaging Physics at the MD Anderson Cancer Center in Houston, Texas. I've been performing MRI research for approximately 20 years, and I've been in the field of NMR, or nuclear magnetic resonance, as well as magnetic resonance imaging for about 35 years. So first, I'd like to describe how a magnet works. We have a superconducting static field coil, which is made up of wires that are at nearly absolute zero temperature, 4 kelvins. And at that very low temperature, the electricity has no resistance in the wires, and so will go around inside the wires for almost indefinitely, and therefore create a very stable magnetic field. Now, inside this very strong magnet, we'll place a transmitter coil that can transmit radio frequencies into the patient. And then we have a receiver coil that detects radio frequencies coming out of the patient. We also place gradient coils within the system that will change the magnetic field very rapidly from head to toe, or from left shoulder to right shoulder, or from the top of the patient to the back of the patient. And that's how we get spatial information, as I'll show in just a moment. And of course, then we put the patient inside the magnet. Now, these magnetic fields are very dangerous if not handled correctly. You can see that this is a 130-pound floor polisher that was picked up by the magnetic field and sucked into the bore of the magnet. Very dangerous. This is unfortunately not an uncommon accident here where a desk chair rolled too close to the magnet and was then very rapidly picked up by the magnetic field and jammed into the magnet bore. This is a very dangerous situation in a hospital where a magnetic O2 cylinder can be brought into a magnet room accidentally and will be ripped from the person's hand who's carrying this oxygen gas cylinder, fly into the magnet. In this particular case, it smashed into a container called a phantom container, and it just, as you can see, had a large amount of velocity that really smashed this container. So very dangerous if the magnetic field is not treated with respect. So 1 Tesla is a unit that is equivalent to 10,000 Gauss to describe the strength of a magnetic field. 1 Gauss is approximately the magnetic field strength of the Earth. I used to work in Tucson, Arizona, where the magnetic field strength of the Earth is about a half a Gauss at 2,500 feet above sea level. Nikola Tesla was quite prolific in the early 1900s in developing a lot of technology for electricity and magnetism, and so we have named this unit of magnetism after him. So what happens if you have multiple Tesla? Well, if you have a 1.5 Tesla magnetic field, which is common for clinical imaging, or a 7 Tesla magnetic field, which is common for small animal imaging, well, then hydrogen atoms, also known as protons, because we're talking about nuclear magnetic resonance. So from now on, I will refer to protons rather than hydrogen atoms. Well, the protons have a magnetic moment that resonates or spins at 64 megahertz. And at a higher magnetic field, those protons spin at a higher magnetic or higher megahertz here at 300 megahertz. So here's an important key. For every 2 million protons within a tissue or a sample, almost all of them cancel each other out. Roughly half are pointing with the magnetic field, roughly half are pointing against the magnetic field. Roughly half are in low energy with the field, roughly half are high energy against the field due to thermal energy in the atmosphere at room temperature. However, there is a net of 9 protons that are pointing with the magnetic field that are not opposed by protons pointing against the magnetic field. So the net signal is 9 out of 2 million. At 7 Tesla, the net is 42 out of 2 million. So you do get better sensitivity as the magnetic field strength increases, which is intuitive. But this shows why MRI is insensitive. For all of those protons within water and other molecules within your body, only a very, very small amount, 42 out of 2 million, are actually generating the net magnetization signal. So I'd like to show a series of schematics first made by Joe Hornack. He has a fabulous website called The Basics of MRI, and I would like to refer to you to that website for more information. And so I really do appreciate his very didactic website. If I were then to show each of the little portions within a three-dimensional volume of tissue or a sample as having net magnetization pointing with the magnetic field, which we call the B0 static magnetic field, you'll see that all of these little components within the tissue, if I were to break them down into smaller cubes within this large cube, they all point with the magnetic field. Well, then I can excite or apply radiofrequency magnetization or radiofrequency excitation to have the magnetization tip to be perpendicular to the initial magnetic field of the magnet, right? And then I can start to collect signals as I'll describe in just a moment. Well, if the entire sample is at 300 megahertz and I apply radio frequency energy at 300 megahertz, that will excite the entire sample. But I don't want that. I want to actually only select a slice within this three-dimensional tissue. So to do that, to do slice selective excitation, I apply a gradient along one dimension so that the magnetization along one edge of this this large volume is at 299 megahertz, and on the other end it's at 302 megahertz. Now I'm exaggerating these numbers for the purpose of this presentation, but it's the same idea when you actually do this in practice on an MRI magnet, just smaller differences in megahertz from the 300 megahertz that is desired. So we apply radio frequency excitation. And while applying this gradient, and the radio frequency excitation is, of course, at 300 megahertz to excite only that slice. But there's a little more extra detail than that we should mention. If I were to apply radio frequencies, which are a pattern of sinusoidal up and down wavelength or frequencies going into the sample, and I turn on that excitation and then I turn it off at a certain time because then I have to do other things during the experiment after exciting the magnetization. Well, if I convolute both of these functions, it would look like this. Over a certain period of time, I turn on my frequencies and then I turn it off. Well, to see what the frequency excitation profile is, I take the time domain presentation and I Fourier transform it to achieve the frequency domain display or presentation. In this case, I'm exciting magnetization at 300 megahertz, but you'll notice that there are these little excitation bands as well at 299 to 301 megahertz, maybe even farther up beyond 299 to 301 megahertz. So I do not get a clean excitation of that slice. Unfortunately, some of the magnetization on the slices next to the slice I desire have also been partially excited. Well, how do we solve this problem? Well, I'm going to now invert the math here. And on the next slide, you'll see that this display down here will be up here, and this display up here will then go down here. So here we go. All right. So if I were to apply this radio frequency excitation, but in a time process where I turn it on and have the phase in one direction and then the phase in another direction and then back, and I also change the amplitude, well, if I convolute both of these functions together, you can see that this is the radio frequency profile that is going into the patient. And if I Fourier transform that time domain signal, this is the frequency domain that is excited, right, at 300 megahertz, this square shape. And this is a Fourier transform pair where the square shape and the sinc function are related to each other. So now I get a very clean excitation of that slice within the three-dimensional volume. And this is a very common concept within MRI to have different pulse shapes that will do different kinds of excitations within the sample. So a lot of research has gone into that over the years. So again, if we have just a slight excess of protons pointing with the static B0 magnetic field in the magnet, and all the other protons are basically canceling each other out, well, I can show that slight excess as net magnetization. In this case, I'm going to say it's pointing along the z-axis. Now, if I apply radio frequency excitation, that's going to cause this magnetization to tip into the XY plane, which is also known as the detection plane. I can start to pick up the signal as the magnetization is only in the XY plane, and I cannot pick it up from my detection system when it's along Z. Well, you might think that the magnetization after applying this pulse would just go back the way it came, but that is not the case. Magnetization, if it's not pointing along the magnetic field of the static magnet, precesses in this helical conformation here to return to equilibrium. And as it's doing that, you can see that the signal is evolving in the XY plane. It's getting smaller and smaller in the XY plane as it reaches the Z axis. But there is a finite time when there is magnetization in that XY plane, projected onto that plane. So let me do that. Let me project what is along the X and Y plane. And you can see that it is this as a spiral coming back to the Z axis right here, getting smaller and smaller in the XY plane. And if I were to plot the y-axis signal, well, it starts at positive right here, and then it goes to 0, right? And then it would point in the negative direction. And then it would go back to the positive direction, negative direction, and so on as it's spiraling around. And eventually it goes to 0. So that's the y-axis free induction decay signal from MRI. Well, if I were to apply a gradient along a sample, in this case a mouse, where on one side it has a very small, very low magnetic field, and on the other side it has a very strong magnetic field, high magnetic field, well, I'm going to get different frequencies. Magnetization does not have much megahertz to it at low magnetic field, as we saw on a previous slide. So you get this pattern. And for other magnetization, I get a very fast pattern. Well, I could just look at the frequencies coming out of this mouse. I can see that right here along this line, if I were to look at all the protons along this part of the mouse, it would have a certain frequency. All the protons along this edge here, well, you can see the edge of the profile of the mouse right here. So it's just like taking the mouse and making a two-dimensional picture as if I were looking at the front of the mouse right here, right? Okay, so that's how we map out one of the dimensions of the mouse. How do we get the other dimension? Well, we have to work on the concept of phase, and this is taken from a publication or a book chapter that I had with colleague Jim Basilian in 2011, if you're interested in that reference. So again, we have this XY plane, and we have the signal evolving in this XY plane as it's returning to the Z axis. And I'm showing that once again as this sinusoid of up-down magnetization, right? What would happen if I also acquired the signal a second time, completely second, different acquisition now? So I excite a second time. But now I allow the magnetization to rotate by 90 degrees, and then I start to collect its signal. Now you'll see that the initial data point is no longer along the y-axis at a positive amplitude. Instead, it starts at 0, right? There's nothing along y when I have the magnetization pointing along x. Let me do that again. But let me rotate it by 180 degrees. And now that signal looks like it starts with a negative amplitude. And so this is the phase of the signal, positive, 0, and negative, and I could continue on and on. In fact, why don't I do that? I'm going to rotate, I'm going to highlight that data point for you, and then I'm actually going to show that it does look like a sinusoid itself if I were to continue this process of one acquisition, a second acquisition, a third acquisition, changing the initial phase of the well, if I do that for 64, 128, or 256 times, we tend to work in powers of 2 because of the Fourier transform mathematics. You can see that this is a sinusoidal signal that goes up and down and up and down in phase. And if I have a 10% slower rate of change in phase, you'll see that these signals eventually do look a little different, right? Here they look about the same. Here they're starting to look a little bit different. Here they're very different, right? You can see that these two data points collected are certainly looking different than this, right? So eventually you see the data that has different phase looks different. Well, I can apply a gradient along a dimension of the mouse. Here I'm going to do this side dimension. So that magnetization at the tip of the mouse nose is in a very low magnetic field. And down here at the feet of the mouse, there's a very strong magnetic field. And by having very low magnetic field, there's going to be virtually no change in phase. But if I have a very strong magnetic field, this is going to whip around by quite a lot, perhaps even more than 180 degrees. If I yeah, might be able to get it to go around almost 360 degrees, right, at this point. And so this is the phase of the magnetization along the mouse from 0 to almost 360 degrees along that mouse. And you can see there's more magnetization here in the shoulders than there was at the tip of the nose and so on, right? So now we can map out the second dimension by looking at phase. Let's add those two concepts together. So I can first very quickly rotate the magnetization by applying a gradient that makes the magnetization basically not go anywhere, zip around a little bit, zip around even more in the center of the mouse, zip around by 360 degrees by this by the base of the mouse here. And then I stop and I apply a gradient along another dimension, and I make the frequency up-down pattern look different left to right along the mouse. So if we were to combine all of that together, I first excited a slice as I showed initially. Then I apply a phase encode gradient to rotate the magnetization, and then a frequency encode gradient along that third dimension to make the magnetization look like it's got different frequencies. And so basically what we're doing here is if I were to look at the magnetization, the protons here at spot A, it would look like this pattern. It has a certain phase and a certain frequency. And the pattern here for the protons in point or circle B would have the same frequency, but a different phase, right? It's different in the phase encode dimension. Here, the magnetization from spot C has a same phase as A, right? Positive, but you can see the frequency is clearly different. And of course, then D has the same phase as B and has the same frequency as C, but is unique in itself. All four of these patterns are unique. And in fact, I could look at any spot within the mouse and find a unique pattern in terms of phase and frequency, and I would know its X, Y coordinates right away, right? And just to show, once we do the Fourier transform of frequencies and phases, we can work out what the three-dimensional or what the amplitude is of the signals at each of these patterns, and put that basically into the matrix for the image that is constructed. So again, I'd like to refer to this book chapter and also these references over here to the left if you would like more information. So the key is slice selection, phase encode, and frequency encode. And if you want to go back and replay this video, that's really the main concepts to identify how we can get information about all three spatial axes for MRI. Okay, so we have the sinusoidal pattern that's going up and down and up and down, and the phase is changing and along the other dimension as well. And of course we've only selected one slice here. And so it's this weird wavy pattern. And if we do a Fourier transform along one dimension, well, we remove that waviness and we just get a peak and it has a certain amplitude, right? And then I can Fourier transform against along the other dimension. You can see it's going down and up and down and up. So I can Fourier transform that sinusoid to find a the frequency information. And so I can map out that this pattern over here on the left is a two-dimensional sinusoidal pattern that is equivalent to this peak in space. And this would be the amplitude of the magnetization within the sample. Of course, if there were other parts of the sample that had protons as well, well, you see a whole bunch of peaks. And in fact, eventually you would see that all of these peaks are really little pixels that make up the entire image. So here is what is called K space, the frequency domain space of all of the magnetization evolving from the sample. First Fourier transform, second Fourier transform. All of these little pixels are like this peak right here in terms of their relative amplitudes. Pretty cool. Center of K-space dictates the image contrast, and the periphery dictates the resolution. So if I were to take the entire K-space, the center and the periphery, and do a Fourier transform in 2 dimensions, you would see the image. And in this case, uh, um, Bach in magnetic resonance tomography took the famous picture of the Mona Lisa and inverse Fourier transformed it to come up with this K-space representation, which you can then forward Fourier transform to look at this image. Now, if we only take the center part of K-space and then Fourier transform that, you can see we got pretty good contrast. There's bright and dark parts of this image. It's blurry because we no longer have these information around the periphery of K-space where the frequencies are changing really fast. They're changing very slowly here, so we don't get a lot of fine detail, but we do see bright and dark parts of this image very nicely. If we then blank out the center, only look at the periphery, now you can see that there is a lot of fine detail here, but it basically looks like the same color gray, right? We've lost our image contrast, bright to dark contrast. So that's important for knowing what to sample, because on this next slide, you can see that we can take the full K-space of a two-dimensional image of the heart, blood vessels. Here's a large artery. I believe this is the aorta. And of course, these are the kidneys right here feeding from the blood vessels. So this is a really nice physiological image of the blood system, right? And going into the kidneys. But you have to collect this entire full K-space to get this image. And we don't really want to spend a lot of time collecting a lot of information. We'd like to make this as efficient as possible for our patients, right? Get them in and out of the magnet as quickly as possible. So let's only take about 60% of this K-space matrix of all these sinusoids. And if I Fourier transform that, you can see that the image quality is still outstanding. We really haven't lost anything, and yet we've saved about 40% of the time for the patient in the magnet. Well, let's do this in a different way and just take out little fractions right here. And again, the image looks really good as well. Um, in fact, if you were to go to Jerry Prince's, um, uh, Martin Prince's article here in 2006, you would see that the image quality might even be a little bit better with the parallel fractional K-space and this slab of K-space that was taken out, but they're pretty equivalent, right? What would happen if we only took 13% of K-space? Well, that's probably a little too much, and you can see it's starting to get blurry. But if all you need to see are these large blood vessels, perhaps that's okay. And again, time is money, and we don't want the patient to have to spend too much time on the magnet. It's not the most comfortable location to be. So that would perhaps be advantageous for some applications. And then finally, about 25% of K-space looks really good to me. It has outstanding image quality and has saved you about 75%, or saved the patient about 75% of their time. Okay, so in general, MRI has some disadvantages. It is high cost, it has poor sensitivity, it is slow, it's susceptible to motion artifacts if the patient were to have some random motion, just randomly move their head in the magnet, or more consistent motion such as heartbeat and breathing motion. So we mentioned the K-space again. I won't dwell on this again. That's from the previous slide. But I want to start with that because it shows that you can take that full Cartesian matrix and reduce the matrix, and you still have pretty good sampling. But what would happen if we then did non-Cartesian sampling? In this case, spiral sampling from the center of the K-space matrix can be done, or radial sampling, or this idea of propellers, kind of like airplane propellers that are at different angles. And so you can sample this matrix and then regrid this information back to an XY Cartesian space, like grid paper, and then you can do your Fourier transform to get your image. The key is that by sampling the center of K-space, where the frequencies are not changing very fast, that reduces the susceptibility to motion artifacts. If you collect a lot of data in this Cartesian matrix, you do collect a lot of data around the periphery, that's going to be more susceptible to motion artifacts. So that's one way of reducing that problem. You can even do compressed sensing and take a pseudo-random series of points within this matrix, again, regrid back to the Cartesian diagram and then Fourier transform. And if you do this discrete wavelet, transform a sparsely sampled k-space with incoherent aliasing, I'd like to refer to this publication for more information. Well, you can basically get a really good image that looks very similar to the full Cartesian image that was taken, which was very, very slow and had to be carefully sampled. While the heart, this is the heart right here, you can see different chambers in the heart. The heart was triggering the full Cartesian acquisition, so the heart was always in the same spot. Well, we measured the heartbeat, or the researchers who were doing this work were measuring the heartbeat and then only taking data when the heart was in a certain location. While here, they could collect data much more quickly, and so then they didn't have to do this triggering on the heart signal and can collect an image very, very fast that has nearly equivalent image quality. What happens if you take k-space lines that are sparsely sampled? Well, if you Fourier transform, you will have an overlapped image. There's just not enough information here to fully recapitulate the full image as shown over here. But you can, if you collect these lines in a well-known place and you know the math behind this, well, you can start to remove this aliasing by having parallel imaging. 4 different images are collected simultaneously by having different detector coils around the patient. And you can then remove the aliasing of this image here, which shouldn't be there, and this image here, which shouldn't be there. And then by doing the math, you can reconstruct and find these points that should be in the real image. So there are different ways of doing this. Grappa parallel imaging is extremely popular on all 7,000 clinical magnets throughout the world now. Really an impressive parallel imaging methodology. And I'd like to defer to this publication if you would like more detail. And so this is a great way of accelerating the acquisition. And you see that the image quality is outstanding relative to the standard Cartesian. With that, I'd like to pause and stop part 1 of this 2-part series and just thank all of the people that I've had the pleasure to work with within the Contrast Agent Molecular Imaging Laboratory, my research group, over the years at Case Western Reserve University, the University of Arizona, and here at the MD Anderson Cancer Center. I can't thank them enough for putting up with all of my crazy ideas. But stay tuned for part 2, which will be available on my YouTube channel as well. Thank you.